So we have finally come to the topic continuous functions. So let's first see the definition. We have two topological spaces here, x and y. The topology on x is tau and that on y is sigma. And we also have a function f from x into y. We will say that f is continuous if for any v in sigma, the inverse image of v under f is in tau. Or in other words, that for any open set v in the space y, its inverse image under f is open in the space x. Now suppose the topology sigma is generated by some basis b. Then for any open set v in sigma, you will find a subcollection of the basis, let's call it b prime, such that v will be the union of the elements of b prime. It comes from a previous result. We got this when we discussed bases for topologies. So from this, what can you say about the inverse image of v under f? That will be the union of the inverse images of these basis elements which come from that subcollection b prime. What does it mean? It means that in order to show that f is continuous, if you can show that the inverse images of basis elements are open, then automatically any such union of open sets will also be open. So it reduces the effort in showing that a function is continuous. You need not show that inverse images of all open sets are open. You just need to verify that for basis elements. And if the basis B itself in turn comes from a subbasis S, then each basis element is a finite intersection of subbasis elements. And so you can write f inverse of B as the intersection of the inverse images of these SIs under f. So this reduces the task of showing that f is continuous even further. Now you just need to check that inverse images of subbasis elements are open in the domain space. That will prove that f is continuous. Next we have example 1, where we consider the type of function that we consider in calculus, and we learn about continuity for the first time for this type of functions. So now we are going to see how this definition that we saw just now is a generalization of our usual definition of continuity of real valued functions of a real variable. So let's consider one such function f. What shall we show here? We will show that if f is continuous in the calculus sense, then it's continuous in our sense also, in the sense of topology, and conversely as well. So we start by supposing that f is continuous according to the topological definition, that means our definition, and we want to prove that then f is also continuous according to calculus definition, that means the usual one. So for that we need to show that f is continuous at every real number. So we choose an arbitrary real number x0 and let epsilon be a positive real number. So now we need to produce a positive delta for which so and so things happen. You already know. So let's start by considering this open set in R, the open interval f of x0 minus epsilon, comma f of x0 plus epsilon. This is open in R because R has the standard topology. When we treat R as a topological space without mentioning what the topology is, it's understood that it's the standard topology. Now since f is continuous, so f inverse of v will be open in R because v is open in this range space R. However, you also note that x0 belongs to f inverse of v. Why? How? Is f of x0 a point in this interval? Yes, it's midpoint. So that's why x0 belongs to f inverse of this by the definition of inverse image. So that's why we have this. But then this is an open set in R. See, this is open in R which contains this point x0. So by the definition of open sets and by the definition of a topology given by a basis, there will exist an open interval a comma b in R which contains this interior point x0 and which is itself contained in f inverse of v. Do not forget that the standard topology on R is generated by the basis consisting of open intervals. Now next you choose a real number delta which is positive and which is also simultaneously less than the minimum of x0 minus a and b minus x0. If we do that, then the open interval x0 minus delta, x0 plus delta will be contained in the open interval a, b, which itself is contained in f inverse of v, so this will be contained in f inverse of v. First of all, how are we choosing this delta? And the second thing is, for such a delta, how do we get this containment? Let's try to understand that first. What do we know about the point x0? The only thing we know is that it is inside the interval a, b. So if you draw the figure, say here you have a and here you have b and x0 is in between them somewhere. Not necessarily at the middle of them, but somewhere. Say in this figure x0 is closer to a than it is to b. And then what does that mean? It means that a is less than x0 and x0 minus a is this distance, the distance from a to x0. Similarly, b minus x0 is this distance, the distance of x0 from b. Obviously both of them are positive, so their minimum is also positive, and you can choose a positive real number even smaller than that. Say this delta, which is smaller than this as well as this. And then you consider the delta neighborhood centered at x0, whose left endpoint is x0 minus delta and right endpoint is x0 plus delta. So obviously this open interval will be contained in this. That is how it's coming. Now let x be any real number such that mod x minus x0 is less than delta. Now we are there. Now we are ready to show that f is continuous at x0 in the calculus sense. So we have chosen such an x. What does this mean? It just means that x belongs to this open interval. But this is contained in f inverse of v ultimately, so that point x will now belong to f inverse of v, which in turn means that f of x belongs to v, and recall that v was this open interval. And that means that the distance between f of x and f of x0 is less than epsilon. So now you are finally there. If this is true, then it implies that this is true. So that means f is continuous at x0 according to calculus. But x0 was any real number, so that's why f is continuous at every point of the real line according to calculus definition of continuity, which means f is continuous according to calculus. And now we are going to prove the converse. So conversely, let f be continuous according to calculus. Now we need to prove that f is then also continuous according to topology, that means our definition. Which means that we need to show that the inverse image of every open set in R under f is open. But actually you need not go to that generality, because the standard topology on R is generated by open intervals. They form a basis for the standard topology, so it's enough to show that inverse images of open intervals under F are open again. Not necessarily open intervals, but open sets in R. So that's why we have chosen any open interval in R. And now let's consider the inverse image. It is something depending on what function f is. But if it happens to be empty, this is one possibility, then we are done, because this is already open in R. So that means now we next have to see the case where this inverse image is non-empty. So let f inverse of a comma b be non-empty. Now you choose any point x0 in this inverse image. It means that f of x0 will belong to the open interval a comma b. So because f of x0 belongs to a comma b, you can choose a real number epsilon which is positive and which is less than the minimum of f of x0 minus a and b minus f of x0, such that the epsilon neighborhood centered at f of x0, that is this open interval, is contained in a comma b. Now there is no need for me to explain this to you because you have seen an exactly similar thing already before. Now f is obviously, this is our hypothesis, f is continuous in the sense of calculus. So in particular it's also continuous at the point x0. So for that epsilon, there exists a delta greater than 0 for which this implication is true. If the distance between x and x0 is less than delta, then the distance between f of x and f of x0 is less than epsilon. What does this mean? It means that if your x comes from this delta interval of x0 centered at x0, then the f image of that x is inside this interval, which is centered at f of x0 and has radius epsilon. But this interval itself is contained in this interval a comma b. So now ultimately what are we getting from this? We get this fact. Because f of this interval is contained in a comma b, so this interval is contained in f inverse of a comma b. But what does that mean? It means that we have found an open interval containing x0 which is itself contained in this set. So that means x0 is an interior point of f inverse of a comma b. But it was chosen as any point from that inverse image. So every point of this set is an interior point, and that is why this is open. And this is what we wanted to show.